All right, so today we'll move into, I'm going to go to chapter 12 in our textbook, from the Spurs textbook. This is on optimization. And optimization, this idea of mathematical optimization or numeric optimization, okay, it's a very big topic, all right, and you can go to Wikipedia and type in, optimization, and it will pull up a whole bunch of related articles and all of that. You can take an entire class devoted to optimization, and actually in 102B we continue further on in the topic of optimization. In our course and in this class, we're really just going to look at two optimization algorithms, two simple ones, and that will be for unidimensional optimization. Okay, so we'll begin with and in your homework assignment this week, you will explore a slight expansion of this into kind of, slightly multivariate optimization, and you'll learn the coordinate descent algorithm. But again, we're only going to just cover this very briefly. It'll get covered a little bit more in 102B, or it should be, but yeah, this topic is very big. Okay, so the whole idea behind optimization is that you've got some function and you want to find the value of x that either maximizes or minimizes the value of the function. And then okay, and so there are, let me just get this. So there are many applications to this. One statistical application is maximum likelihood estimation. Are you guys familiar with MLE, maximum likelihood estimation? Okay, and so the idea behind, just very briefly, the idea behind maximum likelihood estimation is you have some data, D, okay? And you're saying, I think data D is generated by some model, okay? Data is some kind of model. And the model will have parameters, okay? So the model okay, so for example, you might have a whole bunch of data collected on people's heights or something, and you say, well, I think these heights that we're seeing, this is coming from, when I record a whole bunch of people's heights, I think it's coming from a model of a mixture of two normal distributions, okay? And we're going to say we've got a normal distribution for males and a normal distribution for females as far as their heights go, and it's a mixture of these two things, right? So, you know, for example, we can say a bunch of data on heights comes from a mixture of two normal distributions, okay? And so we will have, how many parameters do we have in this model? There is going to be, you've got a mu for males and a standard deviation for males. You've got a mu for females and a standard deviation for females. And then you've got some kind of proportion of mixing, right? What proportion is male and what proportion is female? So this would be kind of your mixing parameter. I'm just kind of setting this up, and then, and according to your model, you would be able to then say the probability of of getting this particular value, you know, is this, right? Because a normal model, you get some kind of density, and then so you can find the probability of getting each observation, and then the total likelihood of everything is going to be the product of every single probability. Okay, so, you know, find the probability of, you know, each observation, and then the likelihood is the product of all the probabilities. Does that make sense? Okay, and so in this case, in maximum likelihood estimation, we would have 5 parameters to estimate, and we would want to optimize the likelihood. We would want to find the set of 5 parameter values that will make this total likelihood, the product of all the probabilities, to be as high as possible, because that's what we observed, right? So if this is what we observed, obviously the probability of observing our data cannot be 0. It cannot be super, super small. And we're going to kind of just say, assume that nothing really strange and unusual happened when we pulled our data, so we want to maximize the probability or the likelihood of our data. Okay, and so this would be an application of optimization where we are trying to optimize this likelihood function by finding the 5 parameter values that maximize this likelihood, right? So that's kind of a little bit more of a complex application of maximum likelihood estimation. We can simplify this down and just say, all right, you know, maybe I observe a whole bunch of people's IQ scores, okay? And we want to know, you know, we're going to say, okay, I'm going to assume that the IQ scores are coming from a normal model, and I want to know what is a good estimate for the mean IQ, right? And here we're going to just say, you know, technically you would have 2 parameters, but we can just say we're just going to try to estimate the mean, right? Estimate the mean of this normal distribution that's generating all of these values that we're seeing. And that would be, you know, a unidimensional application of maximum likelihood estimation. Okay, and there's lots of other applications of optimization, but here's one I think, or at least kind of familiar with this concept of maximum likelihood estimation, right? And then probably in 100B, if you guys took that, you saw that the maximum likelihood estimate for the mean of a population is just going to be the sample mean type of thing, and you probably had to prove that or something. Here we're just taking a kind of a bit of a more numeric approach here, okay? All right, and so, you know, maximization and optimization go hand in hand, and so our algorithms can be written to minimize or maximize a function. And it's no problem, okay, because we just do a little magic trick, not even a magic trick, but just say, let's say you have an algorithm that can minimize your function. Okay. Can you use the same algorithm to maximize it, right? So you're plugging in values and all it can do is just find the minimum, right? And you have another thing and you wish to maximize it. What can we do? Well, the exact same code to maximize our maximize the function by using negative of the function that we're looking for. Okay, and that's all we do. So if our thing is able to, if f of x looks like this, and we're able to find the minimum, okay, and now we have some other function that we want to maximize, okay, and the function looks like this. Well, we can use the same algorithm just by turning it upside down, and then now the minimum here will be the maximum over here. Okay, so we just, if this is f of x, then this will be negative f of x. And then, we wish to find the max, just minimize this. Okay. So we'll start with kind of, one of the basic methods for optimization. All right. And this one is called Newton's method for optimization. Okay, so what happened with Newton's method for root finding? Do you guys remember that? The Newton's method for root finding. Yeah, so you have some kind of function, and starting at some arbitrary point, you take the derivatives and you just get closer and closer and closer. You find the tangent lines at each of these things. If this is your initial point, you take the tangent line, you end up here, and then you kind of zone in, and eventually you get to the root, right? So Newton's method for root finding, you updated your next point is equal to x of n minus the value of x of n divided by okay. So that's Newton's method for root finding. So we can use, so for optimization, we're just gonna say, oh, well, Newton's method is able to find where our function is equal to 0. Okay. Okay, so we can use this for optimization because we know that if you have a smooth continuous function, then the local minimums and local maximums are places where the derivative is equal to 0, right? So we learned this in calculus. So I'll just say, smooth continuous function our local min and local max are locations where f prime of x is equal to 0. Okay? And so to use Newton's method for optimization, we're just going to use Newton's method to find where our derivative is equal to 0. And that's it. So we use okay, and so all we have to do is we just say we can just say let g of x equal to f prime of x, and then using Newton's method we would just say x of n plus 1 is equal to x of n minus g of x divided by g prime of x. Okay? And then eventually this just turns into, it says, okay, f of x must be twice differentiable and then the algorithm for finding your critical values, or where your local mins and local maxes are going to be, is just going to be xn is equal to, or your next point to use will be f prime of x divided by f double prime of x. I'm sorry, x of n. I gotta put that. Okay, is that all right? Just conceptually, does this make sense? So we're just using Newton's method for root finding, and we're just applying it to the derivative, because places where the derivative equals 0 will be local mins and local maxes. Right? And so the biggest limitation with Newton's method is that you need to have a function where you can calculate the derivative, and you need to be able to find the second derivative of it in order to use Newton's method for optimization. And sometimes the function that you're dealing with is too complicated for you to be able to take the derivative twice. Okay? But if you can take the derivative twice, then you can apply Newton's method for optimization. Okay, and so I have just a tiny bit of code here. So let me clear this out, and I put this up. So here we'll load up ggplot. Maybe I should make this a little bit larger for you guys. Okay, and so here my function of x is just x times x minus 2 times x minus 4. Okay? And if you take the derivative of that, you would get 3x squared minus 12x plus 8. All right. I'm going to just create a sequence of x going from -1 to 5. And I'm going to calculate the values y and the values of the derivative of y. And I'm going to just bind all of these together into a data frame. Okay. So here, let me just just plot the function. Maybe we'll do this. Okay, so this is what the function looks like. So, you know, the function is x times x minus 2 times x minus 4, so it crosses the x-axis at 0, 2, and 4, which makes sense. Okay, and we can see that the local max is going to be somewhere around there, and the local min is going to be something around there, right? Okay, and then so the derivative, if I were to plot add the derivative to this, I can add a line, and I'm going to just say in this. So to plot the line, I said we're going to map x to x and y to y, and we're going to add a geom line where the color is blue. Okay, and size is 1. Okay, and over here I'm going to add x is x and y is going to be dy, which is I've calculated to be the derivative of y. Okay, and so here I can just add this, and that's what it looks like. And then just and I'm going to just add a horizontal line at 0, so it gives us a little bit clearer idea of where it crosses 0. Okay, and so we can see that the local max is going to be where the derivative crosses 0, and you know where this derivative crosses 0 is also going to correspond to the local minimum. Okay, and so here we can apply Newton's method, and so Newton's method requires that we calculate f double prime, right? It's going to be a function of x. And what is that? So 3x squared, so that's going to be 6x minus 12x plus 8, so it's going to be 6x minus 12. Right? Am I missing anything here? Oh, thank you. Okay, so that's f double prime, and then and we can just start off with our initial x. So I'll just call this x0, and just starting at any location, maybe I'll start at 0 here. Okay, we can say our next x. So I'll call this. So we'll just say x old is going to be 0, x new is going to be x old minus, and it's going to be f prime of x divided by f double prime of x. Okay. So if I start at there and I plot what x new is, not x, I want x plugging in our x old values, right? Okay, and so this moves me a little bit closer, and then all I have to do is now just plug in, replace our new value becomes the old value, and then all I have to do is I just plug this into a loop, right? So I just say for I in 1 through 10, okay? And each time we run this, I'll just print out x new. This is implementing Newton's algorithm here. Okay, so we'll just starting off with our initial x to be 0, and then I'm going to just run this. Every time we run it, we're going to just update the new value, print out the new value, and then replace the old value with the new one, and then just run it over and over and over again. Okay, and it looks pretty good. It's like after 4 iterations, it seems to have converged right around to 0.8425995. Okay, and that's starting at 0. Okay, what if I start somewhere else? So if I start over at let's say I start at 5. Oops, shoot. I went too quickly. Okay, so we're going to go there, and we'll run that. Okay, and it seems to have, starting at 5, it seems very quickly to converge also around 3.15. And so, you know, it might get stuck if I start exactly halfway in between at 2. I think at 2.1, I'm pretty sure it'll go this way. Okay, but I think at 2, we might error out because I think I'm going to be trying to divide by 0. Yeah. So if you happen to start right at an inflection point, it doesn't know which way to move, right? Because f double prime, we're trying to divide by a 0 there. Okay, so it's gonna complain there. But you know, anywhere else, you move ever just so slightly to the right, it works. Now it's angry. Oh, okay. It'll converge after many more operations. Just because what we're saying is we just started ever so slightly to the right here, and so the derivative at that point is like super flat, and so it's gonna shoot us way off to the edge, and then it has to like climb its way back. Okay, but I think after 20 iterations it would work. Yeah. So, you know, the initial one, it shoots it way off, but then it's like, okay, it's time to return home, and it does. Okay. So anyway, that's Newton's method. The only difference, it's just, so if you get Newton's method for root finding, it makes sense that it'll work for optimization, because now we're just working with the derivative, finding where the derivative equals 0, and that will give us the mins and maxes. Okay. Okay. All right. Are there any questions on that? We're good. Okay. Okay, and then the other one doesn't require any kind of derivative taking. This one is called the golden section search. Okay, are you guys familiar with the golden ratio? Yeah? Okay, so how does the golden ratio work? It's, okay. What is that? Square root of 5. What is it? Minus 1 divided by 2. Also square root of 5 plus 1 divided by 2, right? And the idea is you've got this rectangle. And, you know, we like use the symbol 5 for this, right? And the idea is that you've got this rectangle, and if you cut off a square, over here is a square, and you have 1, 1, and x, the ratios of this thing have the same ratios as this, right? So 1 over x has the same ratios as 1 plus x over 1. Okay? So the long edge over the short edge is the same as the long edge over the short edge, or whatever you want to call it. Okay? And so you know, the golden ratio ends up being something, you know, very close to 1.61 or something around there. Okay? And they say this shows up everywhere in nature. You know, whatever. Okay. And I think European paper is cut according to the golden ratio. Is that true? Maybe? No. I don't know. Maybe not. All right, I'm just making stuff up now. Okay. Okay, so the idea behind the golden section search, okay, let's say we wanted to minimize some function that looks like this, okay? And you know, it just keeps going on. Okay, so what we do is we just kind of set boundaries here. Okay, we're going to say this is x on the left, x on the right. Okay, and then we have two spots, and I'm just eyeballing this, something like this. Okay, and this is I'm going to call this x1, and this one will be called x2. Now I know that seems a little backwards. And the idea is that x1, this is the golden ratio, or 1.61 or 0.61, right? So x1 is about 0.61 of the way over between xl and x to the right. Okay? So basically, so if I've got the d as the distance between x on the right minus xl, then x1 is at xl plus basically the golden ratio times d. Okay? And then x2 is located at x on the right minus the golden ratio times d. Okay? And the reason why we use the golden ratio is because at the if I look at x2 and x1 and xr, here, well, let me just show you what happens, okay, is that so we start off and we say, okay, there's, we want to find the minimum value between xl and xr. And we say, okay, we're going to find x2 and we're going to find x1, and we calculate these values. We find f of x2 and we find f of x1. Okay? And we just compare these values. We say, which one is bigger, f of x2 or f of x1? Okay? And in our picture, we can see, okay, f of x2 is greater than f of x1. Yes?
What is x left, x2, x1, xr? Are those just random?
You just start off with these boundaries, and you're saying we want to find the minimum value of the function that exists between these two boundaries. Okay, so we're just saying between xl and xr, these are just kind of arbitrarily selected boundaries. So maybe you're able to graph the function at some point. Okay, you're going to say, okay, here's the left boundary, here's the right boundary. I'm going to calculate these 2 points which exist in the golden ratio along here. Okay, and we do this, we calculate f of x2 and f of x1, and we find that f of x2 is greater than f of x1. Okay, and what this means is that, okay, well, if if x2 is over here and x1 is over here, then that means the minimum is going to be to the right of x2. Okay, meaning that once I find that a smaller value exists to the right of x1 and not exists to the right of x1, then that means I can take everything here and I can kind of ignore everything over here, because I know the minimum is not going to exist on this side. Okay, the minimum is not over here. Okay, and then so now, after this iteration, x2 becomes my new left boundary. Is that okay? And an interesting thing is that because of the golden ratio, this point x1 ends up being at a golden ratio interval between x1, so if this is now xl, so I should have drawn this a little bit closer. It probably... Let me just slide this over a tiny bit. Okay. Is that this point exists in terms of where the x2 used to be. Okay, so this point is now 60% of the way over, 61% of the way over between xr and x2. So if we just say the golden ratio is around 61%, okay, if initially x1 was 61% of the way between xl and xr going this way, okay, and x2 was 61% of the way between xr and xl going this way. Okay, after I cut it right here, okay, and call this my new xl, then x1 is now, because of the properties of the golden ratio, is now 61% of the way over between xr and the new xl. Okay, and then and we can go, and now we only have to calculate one new point, which will be our new other location. Okay, and so in the in kind of the next thing, see, our thing now looks like this. Okay, so my xl, this used to be the old x2, and I have now a x2. This used to be the old x1. This is xr. This was in the previous iteration. It was the old xr, and then I calculate a x1 here. This is a new calculation. And so we like the golden golden section search, because what this tells us is that every new iteration I only have to calculate one new value. I can reuse the old f of x f of x2. This one already exists from a previous calculation, and I only have to calculate one new f of x1. Okay, and then in this case we see x1 is greater than x2, and so in this case we can throw away everything to the right. Okay, so after in the second iteration, we find f of x1 is greater than f of x2, and so in this case we know that the minimum must be to the left of x1. Okay, so we throw away the stuff to the right. Okay, and then so for the next iteration, this becomes xr, this becomes x to the left, x2 becomes x1, and then we will have to calculate a new x2. Is this okay? No, it's not okay?
What's the first question? What's
Yeah.
the golden ratio? Is it +1/2 or -1/2?
It's they're both. They're both. Okay. So the property. So here, maybe I can illustrate what the golden ratio is. Okay. So here it's so here, okay, maybe closer to 62%. Okay. So I can do 1 divided by the golden ratio, and I'll get 1.618. So there's this thing where, and okay, so 1 minus this is that, and if I do and I divide this by the golden ratio, it ends up being itself. Okay, so this is the property of the golden ratio, is that you can right? So if I say the distance between XL and XR is 1, okay? So let's say XL is at 0, and then XR is at 1, okay? So then X2 would be at the golden ratio, and then X1 would be at 1 minus the golden ratio, right? Okay, so I can see, you know, X1 is at 0.381966, and X2 is at 0.618034, okay? And so whichever side I now reassign to be the new X on the right, okay, so here, let me just kind of illustrate how this is working. So if I have 0, and I have 1, and, you know, this is like 0.38, and this is 0.62, okay? What happens is that if I keep this, okay, if I keep these two at 0.62, 0.38, and 0, this is now from here to here is basically 0.62 of the way over to 0.62. Okay, and so the golden ratio is preserved in all of these iterations, okay, which is nice for us. Okay, and likewise the reverse is also true. Okay, so here is kind of, I've written up some code for you, and so here you start off, you give it some function f, you have a lower and an upper bounds, and then and tolerance will be the point at which it stops. Okay, we calculate the golden ratio, and we're going to say x1 is going to be lower plus the golden ratio times that the distance between the lower and the upper. X2 is that. So the arrangement of points looks like this: lower x2, x1, and the upper. We're going to calculate the function at x1 and x2, and basically, and then so we're saying while the difference between what we're looking for is greater than the tolerance, if f2 is greater than f1, then the minimum is to the right of x2. So then we just reassign all of those things as according to what I described. Okay. Otherwise, we reassign it the other way, and you just iterate between those things. This is, if you read through this, all it is just reassigning what's the lower, what's the upper, what's x2, and what's x1. Okay, so it's very straightforward. And then at the very end, we return halfway in between. Okay, so that's the golden function. And then let me just demonstrate, you know, kind of how quickly it works. You know, let's say I take one of our initial functions, this thing. F is this, and so let's say we want to find the minimum. So right now the golden ratio searches for a minimum, so we're looking for what it's going to find here. So I can just do golden of f. We're going to have one boundary to be 2 and the other boundary to be 5 or 4 or whatever, and it just runs through several iterations, and it minimizes it. Okay, so you know, 3.1547. Okay, right there, which is, I think, right around what we got when we did all the other calculations using the optimize with Newton's method. Okay, so our golden ratio and Newton's method, they agree. They just take different approaches.